Our cavitation engine is the first commercially viable system capable of harnessing the power of cavitation to produce continuous steam energy without a boiler at a fraction of the cost of using conventional, traditional steam methods. The application of this new energy conversion system are very broad. The engine incorporates CES proprietary impact chamber design technology into a scalable steam generation system capable of producing superheated steam for significantly less energy than traditional boilers. Now let me correct myself. Maybe we really weren't the first to do this. Mother Nature actually was.
Far from being quiet, the ocean is filled with a cacophony of animal noise that can even disrupt the sonic transmissions of submarines. Most of the din is made by a surprisingly insignificant creature, the pistol shrimp. By snapping its claws, it can not only make communication sounds, but something far deadlier. These shrimps are its prey. It deals a knockout blow from a distance by using its claw as a sonic weapon. First, its claw is cocked like a pistol, then fired. The effect is literally stunning. As the claw snaps shut, it fires a blast of bubbles. Incredibly, as the bubbles collapse, they momentarily reach the temperature of the sun. This implosion causes a shock wave that stuns.
Prior to launching into a detailed technical discussion of why cavitation energy systems works the way it does, I think it's helpful to know where this is all going. What are the exciting applications? First and foremost, of course, is enhanced oil recovery, EOR, steam-assisted gravity drainage, SAGD, cyclic steam stimulation, and high-pressure cyclic steam stimulation. Then from there, we'll touch on power generation, conventional power generation using rotary expanders, and then the very interesting linear generator applications. From there, we'll touch on how this is important for textile manufacturing. Then we'll get into desalination and water treatment, which also includes the production water. This is the wastewater left over from oil recovery systems, ballast water treatment, and general wastewater treatment. Then we'll touch on marine propulsion, which deals with the interesting phenomena of salt water in our system. Enhanced oil recovery is perhaps one of the most important areas of application for CES. The term enhanced oil recovery, EOR, refers to the technology used to extract crude oil that cannot be extracted through conventional technologies from oil reservoirs. It is also termed as tertiary recovery process, as it takes place after the primary and secondary oil recoveries. Oil extracted via primary recovery accounts for 5 to 15% of the total reservoir, while secondary recovery can extract 20 to 60% of the total oil present in the reservoir. By installing enhanced oil recovery, 35 to 75% oil can easily be extracted from an oil reservoir. To extract the proved reserves, oil extraction companies are pushing the use of enhanced oil recovery in existing oil wells. Thermal enhanced oil recovery technology consumes hot water and steam to stimulate the extraction of crude oil from the reservoir. The commonly used steam injection enhanced oil recovery methods are cyclic steam stimulation, CSS, steam assisted gravity drainage, SAGD, and steam flooding. Steam dominates the thermal technology market and is significant in North America as most of the imported crude from Canada, 35% of all U.S. imported crude, is extracted using SAGD. Per barrel energy costs in producing this oil are heavily dependent on the cost of manufacturing steam. We estimate the CES steam technology can cut the energy required for extraction by as much as 75%, making this oil more competitive in a market which has witnessed wide swings in crude unit prices. CES breakthrough technology will significantly change the various markets using steam because boiler efficiency is an important part of a purchase evaluation, since the annual cost of fuel can be easily 2 to 3 times the installed cost of the equipment. Therefore, a difference in efficiency and the resultant difference in fuel cost, which in the CES case can easily offset the difference of installing the product. In many cases, the fuel savings in the first year exceed the difference of the installed cost of the steam system. This slide deals with the consequences of what happens when the gas bubbles in the expanding cloud of injector vapor collides with the surface geometry of the impact chamber. You can imagine this droplet of water, for example, saturated with expanding cavitation bubbles, suddenly hits the surface of the impact chamber. According to theory, the water hammer pressures that occur within that impacting bubble can exceed, due to the velocity, can exceed in excess of 50,000 psi. Now, the energy, or the thermal energy that's produced when these bubbles collapse, is a function of the ratio of the radius of the uncollapsed bubble divided by the radius of the collapsed bubble, which in this case can be very small, raised to the cubic power. And this can be quite substantial. As you notice in the diagram to the left, you get a lateral jetting, and after the bubble connects with the surface, and of course imagine this happening with tens of thousands of bubbles integrated over 7 jets from the injector. We see the components of the impact chamber. In the upper right-hand corner, you see the impact chamber itself and the containment vessel. Here you see it assembled, and here you see it with the pressure relief valve installed. The entire system surrounded by insulation is there, and now we see it actually operating at approximately 1 injection per second. And you can see each of these injections, by the way, corresponds to 0.275 milliliters of water. And notice the extent of the shock wave and the power of this and how far it is from the impact chamber itself. We are increasing the pulse rate to 3 to 5 per second. In a practical system, this is where we would normally operate. This is one element. Typically, in a 500 pound per hour steam system, you'd have 32 of these units ganged together and under central control by a computer. Here you see it in slow motion. It's like a gun going off,
Mm-hmm. Reminds you of the shrimp.
This is a 4-impact chamber segment of what ultimately will be used as a 32 impact chamber, 500 pound per hour segment. These, what you're seeing here, are piezo injectors. We'll be using hydraulic injectors for this. What follows is an example of a 4-impact chamber unit driving a 20 horsepower V2 reciprocating steam engine, which in turn is operating through a power takeoff and a 12 kW generator. This is an example of the small-scale power generation that the CES is capable of doing. This slide shows an example of a computer-generated model of a rotary expander driving a 1 megawatt generator. As you can see, a system like this in conjunction with our 500 pound per hour steam unit could easily fit in a 20-foot container and be brought to whatever location it was required. CES technology is unique.
No commercial inventions exist that functionally harness cavitation. CES is the only system capable of instantaneously producing steam on demand with significantly less energy than conventional heating. CES can produce steam at significantly less cost than conventional boiler-based methods. CES has comprehensive, strong patent protection covering all aspects of the technology. And our most recent patent, which we expect to be issued soon, has many claims, none of which have been challenged thus far. Cavitation is the only way to generate these temperatures, i.e. the 4,000 to 8,000 degrees C, short of low energy nuclear reactions. CES is the only steam-based system which creates a usable source of energy through a mechanical process rather than internal or external combustion. CES uses just recently available modern technologies which are financially viable, i.e. hydraulic injectors, computer controllers, ultra-high pressure pumps, carbon fiber, and ceramics. CES impacts almost every aspect of modern living: power generation, transportation, desalination, heating, refrigeration, shipping, and so on.